to welcome John Kenney. He's from Toyota InfoTechnology Center in California, and it's industrial troika for this distinguished lecture. So you have experience both from industry and as a researcher, most recently from the publishing in the Proceedings of the IEEE, and also from the VVIC conference, both tutorial and paper, and also very active in standardization, both in Europe and in the US. So it covers all the three legs of this. And the lecture, as very often is the case, whenever somebody comes, everybody wants to take credit for this. So there is actually two presenters of this seminar. It's both an IEEE Distinguished Industry Lecture, which is organized then from the Swedish section of the VT IT-Com societies. And then it's also a Halmstad Colloquium speaker, which means that the speech is going to be recorded and can be available afterwards, like offline on, I don't know, on a link or on YouTube. So, and this is also the reason we were wearing microphones. So yeah, please, I'm very happy that you're here, and we're very interesting to hear about the presentation. I'm not going to talk more about the topic itself. So thank you.
Thank you very much, Elizabeth. And thank you all for coming. I'm very glad to be here today. I was very glad to be invited. I have to admit, my experience with Sweden is a bit sparse up till this point. I don't know if you're familiar with the BBC series on Wallander, the homicide detective. So I see some heads nodding. So I like that very much. It's a very good series. Kenneth Branagh is very good. And of course, I've read the Dragon Tattoo books, and so when I received the invitation, it did briefly pass through my mind that if I came to Sweden, I might be lucky to escape with my life, because it seems that horrible things happen to certain people when they come here. But I've been welcomed very graciously here, and Elizabeth, thank you very much for the invitation. I also wanted to clarify that while the date here, it says that this is April 15 and 16, I'm not planning to talk overnight. This is not going to be an extended talk, but I will give the same version of this talk tomorrow at Chalmers University. So that's what the date is there. And I finally, before I forget, I wanted to mention clearly that this work represents collaborative work that I've been able to be involved in with colleagues, Garth Bonsall and Charlie Rohrs in particular, as well as some others. So with that, I'll begin. I'm going to talk today about some work that we've done in the area of congestion control for vehicular communication, and I'll start with some fairly brief background information, just to hopefully bring everyone to the same starting point. I think probably most of you at least are somewhat aware of this, and then I'll talk about the algorithm that we call the Limerick algorithm in some detail with some mathematical basis, and then that's presented in a kind of an idealistic environment. So then we'll talk about some practical issues that come up with implementing this, and some of the choices that we've made in terms of bringing this into practice. And then briefly at the end, I'll talk about some extensions that we've been able to do and that we're currently working on for the future. So as brief motivation, probably I don't need to go too far down the road of convincing you that that driving is too dangerous, and that anything we can do to make it safer will be worthwhile. In the U.S., in the most recent year that statistics have been compiled, we had over 32,000 traffic fatalities. That's actually coming down, which is good news, but it's still far too large. And there are lots of other costs as well besides those fatalities. With the vehicle-to-vehicle communication technology that we're looking at, the U.S. Department of Transportation has estimated that 81% of the collisions involving non-impaired drivers could be impacted in a positive way by this vehicle communication technology. It doesn't mean that we'll reduce the fatalities by 81%, but it means that we could make a serious dent in it. So as an engineer, it's actually somewhat of a rare opportunity to be able to work on something that can have that very direct positive effect on people's lives, and it's very enriching to be able to do that. Just in terms of terminology, in the US we call this dedicated short-range communication. I know that in Europe that term is often has a affiliation with electronic tolling, and the thing that I'm talking about is more often called Cooperative ITS here. But this talk is a little bit US-centric. So the auto industry in the U.S. and the Department of Transportation in the U.S. have a long history of working together to do research to try to bring this technology into the marketplace. You'll see here a list of a number of projects that have been in the past and that are ongoing, and you'll see the logos of 8 automotive manufacturers, including my company, that are currently working together. It's a little bit unusual for these companies to work together. We're normally competitive, but in this area, partly because of the importance and also partly because it is by its nature cooperative and standards-based, it's much more productive for us to work together. We don't really have proprietary interests in most of the technology. So we work closely. I work closely every day with people from all of those companies, and it's very enriching. So at a very high level, how does it work? In the US, we have this thing called the basic safety message. In Europe, there's an analog to that called the cooperative awareness message. This basic safety message is sent out in a broadcast manner wirelessly by each vehicle nominally 10 times per second in the US, and it includes all of the core vehicle state information: where the vehicle is, how fast it's traveling, its acceleration, what the status is of various brake systems, how big the vehicle is. A lot of this information, and it's broadcast, as I said, up to 10 times per second. All of the vehicles then that are able to receive these can process these messages and can model where the other vehicles in their surrounding area are. And by doing that modeling and comparing trajectories of where the vehicles will be traveling in the future and comparing with their own trajectory, they can predict, identify and predict potentially hazardous, potential collision kinds of situations. When a situation like that is recognized, then the vehicle, the system in the car can provide a warning to the driver, or even maybe in the future take control of the driver. So here I've just illustrated one of many crash scenarios that we can address with this kind of communication. Let's say there's a stopped car, maybe it's disabled, maybe it's just stopped in traffic, and it's providing this DSRC communication. This car back there that's traveling toward it will get those messages and will do this modeling, and will be able to help the driver if for some reason the driver doesn't recognize the danger of the situation. Maybe the driver isn't paying attention, or maybe their vision is obscured by a truck or by fog or something, but this communication can help bridge that gap and prevent the collision. So that's the very high level of how it works. One thing that's a key from a technology point of view, and I think this will show up on this slide. I'm actually going to take this briefly out of order. This is a look at the protocol stack for this type of DSRC communication. And here what we have at the bottom, at the MAC and physical layer, is 802.11, what we call 802.11p. 802.11, as you know, is the standard Wi-Fi technology. We made an amendment called 802.11p in 2010 that's specifically focused on the vehicular environment. It isn't actually that different, though. Most of the protocol is the same as regular Wi-Fi. It does allow for faster engagement because the vehicles can't take time to associate and join a wireless LAN. It simplifies that process, but it's largely standard Wi-Fi. And then we have a number of other protocols which I won't talk about today that come from the IEEE 1609 working group and from the SAE with regard to application performance and message formats. So the 802.11p, though, will be important for what we're going to talk about today. So let me just go back and talk briefly about where does this technology stand. We've been researching this now. If you looked at that project list, it goes back about 10 years. Some people have been working on this even longer than that. I've been doing this for 6 years. In the U.S., the organization that's responsible for regulating vehicle safety is called the National Highway Transportation Safety Administration, or NHTSA. They have announced that by the end of this year, they're going to make a decision about whether this technology is important enough and shows enough benefit to be required in new vehicles going forward. So we're all in the U.S. kind of anxiously awaiting for that decision. If they go with this regulatory mandate type of approach, then that will dictate how the market will unfold. If they don't, then it will unfold in a more voluntary type of way, which is the way it's happening here in Europe. So we'll see, but probably there will be a mandate for this, and in some years, it'll still take a few years before it starts appearing in cars, but that's the roadmap that we see for deployment in the U.S. Okay, so coming back to the 802.11, this graphic here, and unfortunately this is a little bit light over here, but this helps explain the motivation for the type of approach to congestion control that we've taken. What I'm showing here in these two side-by-side graphs are standard 802.11 MAC types of behavior when the channel is excited with periodic messaging of the type that we have with our safety messaging. Now there could be some other types of thank you. There could be some other types of messages besides the basic safety messages on the channel, but the congestion is going to be primarily due to these basic safety messages. So what we did was, this data is the result of some experiments that we did with radios. We took 30 radios, but we asked them each to emulate a number of additional radios so that we could send more than just 30 times 10 messages per second. And we measured how many of those messages were successful. And the topology was a fairly close-in topology, but we used attenuators to emulate distance. So there were a few hidden nodes, but not too many. And so what we saw was that as the number of messages in aggregate went up per second, which is the x-axis here, the throughput went up until it reached a maximum point, and then it started to come down. And this is a very well-known phenomenon in 802.11. The peaking there, the reason it doesn't keep going up is just simply the bandwidth is exhausted. And if you know how 802.11 works with the CSMA MAC, what happens is that these uncoordinated transmissions end up overlapping with each other. They end up having frame collisions, and those frame collisions lead to lost packets. And when the offered load gets too high, there's so many, the probability of a collision gets to be so high that throughput actually begins to go back down again. So this is really quite important for understanding how to manage congestion. Corresponding to that curve, what we have over on this side is what the actual probability of the packet being lost is, and also what the channel activity or the channel busy ratio is for each of those offered loads. So we see here that the packet error rate curve is also increasing, although not quite linearly. It kind of goes through an S-type shape. The channel busy ratio increases monotonically, but it begins to approach 100%. And so one of the conclusions that we reached when we looked at that is that the maximum throughput is occurring for channel busy ratios that are roughly between 60 and 70%. Now, this is for a certain packet size and so forth, but we think that this phenomenon would be true for a wide variety of the types of packet lengths that we might see in this kind of environment. And also, even though we're using 30 radios to emulate larger numbers of radios, we've done some simulation work to validate the fact that these numbers would be approximately true, even if we had a large number of vehicles sending 10 messages per second. So that's the first thing to realize. And if we look at the areas of channel busy and packet error that correspond to those maximum throughput range, one thing we realize right away is that the packet error ratios that we should be striving for if we want to have high throughput are not 0 or 5% or 10%. It's okay to be having a fairly moderate to high level of collisions happening if your goal is to maximize the throughput of these messages, which loosely speaking is what our goal is. And And so I say that because there are some people whose natural inclination in this area is, let's use the channel as little as we think we need to. Let's only send messages when we are quite sure that the message is important. Our philosophy is different. It's, let's use the channel in a healthy way. Let's use it a lot. Not too much, but let's use it a lot. Let's not use it too little. So that leads us to an approach that says, well, if we can achieve channel utilizations in the order of 60 to 70%, we're probably going to be getting about as many packets per second through this channel as we can. Okay, so that takes us into the second part of the talk. Now let's talk about what we can do to handle these congested channels when they occur. There are a lot of different knobs we could turn, if you will. There are a lot of different things that one could try to control, and I've just shown 5 of them there. Believe it or not, there are even more than that. But out of all of those, the one that we are most interested in, the one that we have emphasized, is this first one, the message rate knob. So we want to control the rate at which messages are being sent by each vehicle. When there's a relatively low load on the channel, then each vehicle can send a large number of messages per second. We typically will cap that at 10. There's probably not much point in sending more frequently than 100 milliseconds. But when the density of vehicles gets high enough that that 10 messages per second would lead us to get on the wrong side of the throughput curve, we'll scale back and we'll try to keep the overall channel load in that 60 to 70% range, which gives us the best throughput. And there are a number of a number of reasons that I've listed here for why our focus is on message rate control. I'm not going to go through that list, but it is a topic. It is a topic maybe for another day or another venue, because there are people whose natural inclination is to say, let's control the transmit power or let's control the bit rate, and all of those things have some validity to them. But we think for a single control that message rate is the best one to follow. Okay, so that takes us into this realm of distributed control. And what I mean by that is that we want a system in which each vehicle can act autonomously, but in a way, because it's following a common protocol, in a way that coordinates with what other vehicles are doing and will lead to an aggregate solution that will be effective for what we're trying to do. So each vehicle will run a message rate control system that produces a rate, R sub I, and all of the vehicles that are in a neighborhood, if they do that, even though they're doing that in a distributed way, those rates are coming back together into the channel to produce some sort of overall channel busy ratio like we saw on that slide, and then that can be measured and feeds back into these vehicles. So this is kind of the high level of what our distributed control system would look like. So that leads us to a decision of how do we want to actually implement the control. So people who have done work in congestion control will probably realize that in most cases, and this is not a new topic for networking, but in most cases the control approaches that have been adopted use what I'll call a binary approach. A good example of that is TCP and the internet. In TCP, if you remember, you control the size of your congestion window, and it's a simple control. If you get an acknowledgement in time before a timeout expires, then you're allowed to increase the size of your window. If the acknowledgement doesn't arrive, you contract the size of your window, and that's how you try to modulate your use of the channel. And so you're always going up or down. You're always changing, and that's a characteristic of binary control, is that it has a natural oscillatory nature to it. This is not a bad thing to do. This is a good choice in general, especially if the nature of the thing that you're getting your feedback from is itself binary. In the case of the TCP, it is. However, what we recognized is that there could be some advantages to following what I'm calling a linear control approach if we can get feedback that isn't binary. So just to introduce some notation and terminology here, our algorithm is going to have the goal of controlling the channel load, keep it in that 60 to 70% range, And we're going to do that initially by defining a goal in terms of an aggregate message rate among all the vehicles in a neighborhood. We'll call that R sub goal or R sub G. And then and we're going to use R sub T with no subscript to represent the sum of all of the rates of the message of the vehicles in the neighborhood. All of the R sub I's added together equals R with no subscript. And then if we were using a binary approach, we would simply ask the question of whether our goal is greater or less than RT at a given time. And we would go up or down. We would increase our individual rates or decrease our individual rates depending on the outcome of that question. But with our linear control, in what we call our limerick algorithm, linear message rate integrated control, we're not going to just do that binary question. We're going to instead compute the difference and use the whole number, use that entire adaptive error in our update. By the way, I meant to say at the outset that questions are welcome anytime and also at the end. So whatever you feel more comfortable with. If there are any questions, I'd be glad to field them at any point here. So maybe this is a good point just to stop and ask. Are there any questions so far? I'll pause an extra long time and take a drink of water just to tell you I'm really serious about questions. Okay, so limerick is the name of our algorithm. By the way, let me just cultural reference check. Do you know what limerick? Does the word limerick mean anything to you?
Ireland.
Ireland. It's a city in Ireland. Anything else? It's also a type of poem. That's right. Very good. I learned, so I'm the one who came up with this acronym, and I learned shortly that my colleague Gaurav, who's Indian, had no idea about either of those two references. I was very proud of this acronym. Of course, the real limerick has a K on the end of it, and I couldn't come up with something to make a K out of it. But yes, so it's a city in Ireland, and it's a type of poem. Unfortunately, some of those poems are a little bit off color, but if you do a search on the internet, you'll find that out. So I don't like to go too far down that road. Okay, thank you. So, we're going to now introduce the limerick algorithm. As I said, we're going to start by introducing it in an idealized environment where we assume that all of the vehicles are within range of each other and they all can sense what the aggregate rate is that is being used by other vehicles, and then we'll relax some of those assumptions later when we talk about the practical issues of implementation. This is just a repeat of what our goal and RT are and the adaptive error. We've seen that in the last slide. So this is the update equation that we use in limerick. At any given update time, the jth node will change its rate according to this formula. So it'll take the previous rate and it will multiply by 1 minus alpha, where alpha is an algorithm parameter, and then it will add to that another algorithm parameter beta times the difference between RG and the aggregate rate at that time. So if you remember from the previous slide, that difference in the last part is what I'm calling the adaptive error, and that's the part that we're using in its full precision, not just in a binary way. This is where the linear term comes from. Beta is a positive parameter that I'll call the linear gain parameter. It has impacts on stability and convergence speed. We'll look at the stability aspect in a detail in just a moment. And alpha, which I call the contraction parameter, is between 0 and 1. It also impacts convergence speed. It has a smaller impact on stability, and it has a large impact on fairness, which we'll talk about in the next few slides as well. So this is the limerick algorithm in a nutshell, in one equation. So to understand its properties, let me just briefly go into a little bit more math. Since this is an academic environment, I feel free to do this. Usually I skip this step. But if we look at, we can construct a state transition matrix that looks at the ways that the update for rate for node J is impacted by the rates at all of the other nodes, the R sub i's at the other nodes. That's what this matrix captures. So, for most of them, the relationship is that the R sub I contributes to the adaptive air, and so there's a minus beta multiplier. But for the self transition, it also has this contraction term in it. So that's a pretty simple state transition matrix. If we let B be the vector of all the betas and R be the vector of all the R sub i's, then we get this state transition equation down here, which is pretty nice and simple for a linear system. So as linear systems go, as adaptive controllers go, the analysis of this is actually going to be pretty easy. What we know is that since it's a discrete time linear system, if we can become convinced that all of the eigenvalues are inside the unit circle, then we will have stability. That means that that when excited by a constant R sub g, it will converge, and it will converge to a unique solution. So then we just need to ask if this is true for the eigenvalues, and if so, what is the solution to which it converges? And I won't show the analysis, but it's not too hard to show that it has k minus, if k is the dimensionality of the system, in other words, there are k vehicles, it has k minus 1 eigenvalues at 1 minus alpha, and 1 eigenvalue at 1 minus alpha minus k beta. And because we've assumed that alpha is between 0 and 1, these are all by definition okay. So the stability criterion really just comes down to satisfying that that term is within the unit circle, or if we rewrite it, it looks like this. Alpha plus k beta has to be less than 2. If that's true, then this linear system will converge to a unique solution. So what will it converge to? Well, again, skipping some steps, but I'll just tell you that you can get here pretty easily by just assuming a steady state condition and doing a difference equation on the update. It's not too hard to believe what I'm going to tell you, which is that this is what the individual rates will converge to. Now, just to give you a little bit of intuition, that's not exactly what we wanted it to converge to. When I said RG was the goal, that's for the aggregate rate that will be used by all the vehicles. And so that means that each vehicle, ideally, would have a 1 in k share of that. So we might have expected to see RG over k. That might have been expected to be the ideal case. And instead we have these alphas and betas in here. But if alpha is small compared to k beta, then we'll be very close to that target. Okay. If alpha is larger compared to k beta, then we'll be a little bit low. So we sometimes call that the bias in the adaptation. I'll talk about that maybe just a little bit. But one thing I can say is that if there's a range of k for which you want this to work well, you can inflate your RG actually to account for the bias, and you can get to the approximate level that you want. In practice, we don't find that to be a problem, and part of the reason is that in practice, it's larger values of k that we're interested in, and for that, the alpha is small compared to k beta. Okay, so one thing to immediately notice is that that all of the R sub j's are converging to the same thing. So we have fair convergence. In other words, the wireless resource is going to be distributed in an equal way among all of the participating nodes, under the assumption that they can all sense the same aggregate message rate that's being used. And I want to talk a little bit about time of convergence. One thing that we can do is we can do a difference equation on R sub j and R sub k, and we see that that initial conditions that might be different between them are forgotten with a 1 minus alpha to the t factor. So that's the speed with which fairness is achieved. The rates come together, and then the aggregate rate converges to this, which is just k times that, with a speed of 1 minus alpha minus k beta. So that doesn't really give you a lot of intuition, but what it tells us is that we can choose the alphas and the betas to achieve the right kinds of trade-offs we want between convergence speed and this bias term. There are other things that impact as well. Assuming that we've already achieved stability, alpha plus k beta less than 2, we can also manipulate alpha and beta to achieve a trade-off between convergence speed and bias. Okay, so this just illustrates in practice, this is an NS2 simulation of this algorithm. We chose, this is for a case where we have 180 nodes, but we look at, in particular, 4 of them, and just for fun, we set them all to have different initial conditions. And what we wanted to see is, what does the convergence look like? You can see here the fairness and the fact that they're all coming together. You can see the relative speed of convergence. This is in numbers of iterations. And then the fact that we can prove this is a very strong characteristic that helps us believe that this is going to be a good thing. I'll just mention that this was published at the Vinet workshop in 2011. And we've got a submission at Transactions on Vehicular Technology that expands on this, that we're hoping will be published later this year. Okay, so one of the things to notice about that is that it also converges exactly. These things all come together just to whatever the precision of your computer is, that's the extent to which you can achieve exact convergence. And we can contrast that with what we might have gotten if we had just used a binary control, where we only looked at the sign of the adaptive error instead of using the whole adaptive error. So for example, if we used an additive increase, multiplicative decrease type of approach, like is used in TCP and lots of other congestion control, those are going to converge to a limit cycle that looks, in this case, like this, with 150 nodes. So one of the things that we're able to achieve is getting away from that limit cycle behavior as an inherent characteristic of the algorithm. That's one of the good things about Limerick. Okay, so that's the idealized version. Now I'd like to transition to talk about what some of the practical implications are for implementing this. And those have to do with how we choose our parameters, what the stability is, and what happens if we don't meet the criterion. And I won't go through the list here. I'll talk about each one of those points. So choosing the parameters. As I've mentioned, alpha and beta affect a lot of different things. First and foremost is stability. Alpha plus k beta has to be less than 2. Okay, and that's our first priority. But once we've achieved that, there are other things that we can trade off. And I mentioned the bias. Here I've called it steady state mean, but that's the bias I was talking about earlier in the speed. I didn't talk about variance, but I'll come back to that later. So one of the things to realize is that meeting this stability criterion is not a trivial thing to do, because we're operating in an environment where we inherently don't know ahead of time how many vehicles there are going to be. We don't know what K is. If we knew what K was, it would be easy. We would just say our aggregate rate, our goal, just divide it by K, and everybody uses that. So we don't know that, and we don't want to assume that we can really accurately estimate that. So what do we do about that? Well, there's a couple things we could do. One thing we could do is we could try to adapt alpha and beta in a slow adaptation loop to track K, so that we can keep it in a stability range. And that's something we haven't pursued too much, but it's an area of potential research. What we have done is we've looked instead at a way to guarantee stability with a static choice of alpha and beta, and that's what I'm going to talk about next. So what do we do? First of all, we say, let's think about the range of values of K that we want to work well for. Small values of K are not a problem, because that means the channel's not congested in the first place. So we don't need to optimize for small K. Very large values of K could be a problem, but they're probabilistically unlikely. So we want to make sure that when those occur, when those rare cases occur, the algorithm doesn't fail, it doesn't become unstable, it doesn't dramatically stop working, but it's okay if there's a little bit of degradation. So that leaves us with a range of values of K that we want the algorithm to work well for. In our sort of somewhat arbitrary choice of that, we said let's assume that congestion nominally starts at about 150 vehicles. And so we're going to choose to optimize around that point. So we set beta to be the inverse of that, 1 over 150. Okay, and then in most of the simulations that I'll show you, we're using that value of beta. We also somewhat arbitrarily used a forgetting factor of 0.1 in the contraction term. That seemed like it's a reasonable place to start at least. Okay, so and as I noted earlier here, when the values of k are much less than 150, it looks like that's bad because we'll get a big bias term here, but in fact, the rate we would be converging to would be very high on a per vehicle basis, and we're probably going to clip that at 10 hertz anyway. So we don't really worry about that high bias for small values of k. Okay, so with those choices of alpha and beta, then our stability bound becomes k less than 285. So nominally, we're saying congestion starts at 150 vehicles, and we'll be able to function exactly as I've shown you now for any number of vehicles up to 285. But what happens if you go above 285? For example, if you were at 300, then the system becomes unstable. The adaptive algorithm doesn't work. So we introduce something we call gain saturation to handle those cases when the k becomes larger than the stability bound. So with the limerick, as I've explained it to you so far, we use the multiplier on the error term is a constant beta. So the update beta e is linear in beta. No matter how big error is. But with gain saturation, we say we're never going to let the beta e term have too large a magnitude. We're going to cap it above and below. So if beta e, we'll compute beta e, but if it's above this or if it's below that, we're going to use those what we call saturated values of gain. So then that introduces nonlinearity into this linear system, and what will happen then is that, let's say we're above the stability bound again at 300, we're above 285. When we do it with gain saturation, instead of having this, total instability, we converge to a limit cycle, just like, similar to, I shouldn't say just like, but similar to what you would expect to get with a binary control like AIMD. So we have stability. Yes, there's a limit cycle, but we can tolerate that. This is the slight degradation that I was talking about for those relatively rare cases when we have so many vehicles. Now, whether 285 is the right threshold or not, that's something we have to study. But we can adjust our beta. If we decide 400 is the place that we want to be good up until, then we can choose our beta to be, say, 1 over roughly 200, and then that becomes the place where gain saturation would start to kick in. So that's one of the practical aspects of implementing this, is that we put gain saturation in place to handle the fact that we don't have an upper bound on k, and yet our stability depends on that. Another one has to do with how the updates are coordinated among vehicles. What I showed you so far assumed that all vehicles are making their update decisions at the same times, and they're measuring the aggregate rate offered in the channel at the same times. That's okay, we can achieve that because we can synchronize the vehicles, but an alternate would be just to say they're all going to use the same period, but each with a random phase. And we call that the sequential update case. That's easier to implement because you don't have to have the same degree of synchronization. And it turns out that actually improves our stability. We had a conjecture that this would be true, and then we did some analysis, the math for which is actually really ugly. And at the end of the day, we're left with something a little bit less than a fundamental proof. We're left with very strong evidence, I'll say, that the conjecture is true, and that not only does it improve stability, that the stability criterion, instead of becoming alpha plus k beta less than 2, just becomes alpha plus beta less than 2. There's no k term in that stability criterion with sequential updates. So the intuition behind that is that when everybody is updating at the same time, then the aggregate rate is taking big steps. All k vehicles are moving in the same direction by the same size at the same time, and so the aggregate rate is going up in a big step or down in a big step. And when you do it sequentially, you'd have a series of little steps, and it's fundamentally more stable. So this is an advantage that we see. There's a caveat there that I'll come back to later. And so now here's that same 300 vehicle simulation. We have the gain saturation in here, but we don't need it anymore. With sequential updates, we get the nice exact convergence that we had, even though we're above what would have been the stability boundary for the regular limerick with synchronized updates. Okay, a third practicality is, as I've introduced this to you, I've said, let's assume that we have a goal for the aggregate rate that all the vehicles are using, and let's assume that everybody can measure what the current aggregate message load is from all the vehicles. Well, that actually would be difficult to do, that latter thing. To measure what everyone is currently using for a message rate would be difficult, but what's easy to do is to measure the actual channel busy ratio at any given time. And in fact, this is really more like what we wanted anyway. As I showed earlier, we have a target of having a channel busy ratio between 60 and 70%. So when we actually implement limerick, we're not going to use an RG, we're going to use a CBRG. We're going to have a goal for the channel busy ratio, and then instead of plugging into the adaptive error the current aggregate message rate, we're going to plug in the current channel busy ratio, CBR of T. So that's, and the fact is there's a one-to-one, and for the range that we're interested in, nearly linear relationship between those terms anyway. So we're going to use this adaptive error instead of this one that I showed you earlier. In our practical implementations, it really doesn't change anything. Okay, but when we're using a channel busy ratio in the implementation, when I said we're going to use what the current channel busy ratio actually is, now we come to an estimation problem, because I said it's easy for us to know that. Well, I should have said it's easy for us to know that within some noisy estimate, because what we're going to do is we're going to measure it over some finite interval, and that finite interval isn't going to be long enough to know exactly what it is. So one way to think about this is that we can model the adaptive error as being the difference, not just the difference between the goal and the actual CBR, but with a noise term, WJ, which for our purposes we're going to at least start by modeling as a white noise sequence with zero mean and a variance sigma squared. So what we've done is we've said, if that were the right model, what would the math tell us about what would happen? Well, when you have that noise term in the adaptive loop, it creates variation in the steady state condition of the message rates. They no longer converge to a precise value. They converge to something with a constant mean, but with some non-zero variance. So we've done some analysis to model what the mean and the mean square are, and the mean turns out to be just what it was before. I've changed this from the R sub G to CBR sub G, but otherwise this is the same thing that we had before in the deterministic case. And I'm not going to show you the messy equation for what the mean square looks like, but it's proportional to sigma squared, which is not surprising. So the better we can estimate CBR, the less variance we'll be inducing in our rates. So that tells us something about what our intervals should be. In practice, in our implementation, we typically use 200 milliseconds of CBR measurement. Sometimes we do an extra level of averaging on that, and that seems to induce about a peak-to-peak 1 Hertz variation in the message rates, which we deem to be acceptable. If that wasn't acceptable, then we could modify that. This isn't just a function of sigma squared, by the way, it's also a function of alpha and beta. So this is another thing that the alpha and beta can be used to trade off. If we use smaller adaptive gain, for example, we'll get less variations in steady state. I think I'll keep going here because I think we're running out of time. This is a simulation showing what happens when you use a noisy estimate of the channel busy ratio instead of an exact aggregate message rate like I showed you earlier. And as I said, you get approximately, in this case, about a 1 Hertz peak-to-peak variation in steady state. But it still converges. It's still fair. Okay. Now I want to get into the kind of the last important part of the discussion, and that is, one of the biggest constraints of what I've assumed so far is that all of the nodes could hear each other and could measure the same, in this case, channel busy ratio. We know that in general that's not going to be the case. We have long roads where some nodes are hidden from others. They'll be sensing different levels of channel load. What happens then? Well, our colleagues at Karlsruhe and at Mercedes North America have been looking at that problem not with respect to Limerick initially, but actually with respect to an AIMD algorithm. And what they found is that if you only update based on local channel busy ratio measurements, you can have an unfairness situation that's shown here. So this is a long road, 5 kilometers, and this is the steady state rate to which all of the nodes are adapting with AIMD when you don't do anything special. And you can see that some nodes here in the middle are being driven all the way down to 1 hertz. These that aren't experiencing so much channel load are happily going at 10 hertz. What they found is that if the nodes will share information about the channel busy ratio that they're measuring, then they can achieve a higher level of fairness or a better distribution of the channel resource. And as you can see over here on the right. And their algorithm is called Pulsar. And we can see in this particular example, there's about a 4 times ratio between the minimum rate here and the minimum rate here. So this worst off vehicle is getting 4 times the message rate that it would have without Pulsar. So, and there's a reference to their paper. So we looked at that, and we've been talking to these people for a long time. And we said, okay, let's try to bring this idea together with Limerick. So the Pulsar information sharing protocol can be coupled not just with AIMD, but with other types of adaptation. And in fact, the unfairness that they found isn't particular to AIMD. It's really inherent in any of these types of adaptation. And so we said, let's marry Limerick and Pulsar together. Well, when you do that, that means that you're going to in their version of Pulsar, all we had to do, each node just had to tell everyone else whether they thought the current level of congestion was above or below the desired threshold with 1 bit. Now we want to share the full precision of measured CBR, but that's not too much of a problem. It just means more bits have to go into the header. But then the question is, how do we use the information? In the original Pulsar, you just take all of those congestion indicators from your neighbors, and you say, I'll just do a logical OR. If any one of my neighbors is congested, I'll act as if I'm congested, and I'll reduce my rate to try to reduce my contribution to that congestion. By the way, I should have said that Pulsar distributes this information over the interference range of the node of the receiving node. So anyone who's contributing to that congestion should also be receiving this indication and can contribute to the solution. So instead of just taking the logical OR of all of these 1 bits, we decided to take the maximum of all the CBRs that we receive from our 2-hop neighbors, and we put that into our Limerick plus Pulsar. This has now been implemented in the US in a research program, and it's been tested and shown to work. It's a program that I don't have the authority to disclose results of, so I can't go into any more detail than that, but I can tell you it works. Okay, now there's one complication though that's introduced by this Pulsar information sharing. In order to make it work, they delay the application of the CBR measurement by 1 or 2 cycles, so that while I'm waiting to hear what my 2-hop neighbors are experiencing, I also wait to use what I'm experiencing locally. If the biggest congestion in my neighborhood is measured by me directly, I don't use it immediately, but I wait 2 cycles to use it, or I wait 1 cycle to use it, depending on the various. There's a modified version of Pulsar that only requires 1 unit of delay. This is important for Limerick because when you inject, this is delay we'd be putting into the adaptive control loop, and when you put delay into an adaptive control loop, it impacts stability. So whereas before, when we didn't have any extra delay, and when we chose alpha 0.1, our stability constraint was k beta less than 1.9, if we introduce 1 extra unit of delay, it comes down to k beta less than 1.0, and if we have 2 extra units of delay, it comes down to 0.64. We actually found this out the hard way. We did some tests without modifying it, and guess what? We went into the gain saturation when we didn't think we should be. And then we did the analysis and figured out why. So we didn't change Limerick, but we just had to use a smaller beta so our k betas would stay under these smaller upper bounds. It's also true that this delay reduces the advantage of the sequential update that I showed you earlier, unfortunately, because that was a nice thing. So we're looking for ways to get that back. Okay, just to wrap up then, there's some other things that we're looking at right now to extend these results. One of them is a weighted fare version of Limerick. Instead of everybody converging to the same R sub I, we would like a way for them to be able to converge to a weighted fare, so that if I desire that node 1 have twice the rate of node 2, then I can achieve that. And we've shown how to do that through choice of alpha and beta. And we're going to present a paper on that at YVEC in June. Another important topic is why should we actually give all vehicles the same rate? And are there situations where momentarily a vehicle has a higher need for extra transmissions, for transmission opportunities, perhaps because it's changing lanes or it's accelerating or it's an emergency vehicle. These two in particular, these dynamics mean that it's momentarily hard for other vehicles to track where it is or where it's going. So the consequence of too big a gap in reception from that vehicle would be high tracking error and could lead to failing collision avoidance applications. So there may be times when we want to give extra transmission opportunities. We could use this weighted approach, but that probably would adapt too slowly to these very fast changing things. So we're looking at other ways to try to identify when extra opportunities are needed and to give them, and we have some ideas about that. And then finally, kind of an open topic is how to combine these rate control type of mechanisms with the existing quality of service mechanisms that are already embedded in 802.11 chips called EDCA. I think that's an interesting research problem that maybe somebody would want to take up. So to conclude, we've introduced the Limerick algorithm. The salient characteristic of it is that it uses all of the adaptive error, not just the sign of the adaptive error. So it's not doing binary control, it's doing linear control. And in our simplified environment, it has very strong provable convergence and fairness and stability conditions, which gives us a lot of confidence when we implement it. It avoids the limit cycle behavior because it's not binary. And when we look at some of the practical issues that come when we deviate from the ideal case, it still works fine. So it's not hard to choose a static value of alpha and beta. We don't have to adapt those. We can use gain saturation to guarantee stability even if we have low probability high density cases. We could use asynchronous updates, the sequential update thing, to be robust, although the advantages of that are questionable when we're also using pulsar. We can combine it with pulsar to achieve global fairness. And then finally, when we're measuring channel busy rate in a noisy way, we have good math now to explain what sort of variation that will induce to the adaptive rates. So with that, I'm done, and I'd be very glad to take any of your questions at this point. Thank you. Thank you. Yes, young lady.
Yes, I have a question about Limerick. The proposal of Limerick from the beginning didn't include information sharing. Is that correct?
That's correct. That's correct.
Oh yeah. We need to repeat
the question was, is it the case that in the original conception of Limerick, it did not include the information sharing of the channel busy ratios? And that the answer is yes, it did not. So that came to us from the Pulsar, our colleagues who were doing the Pulsar work. And that was their idea, and it was a good idea, and we've been able to adapt it successfully.
So it was only based on the local channel busy?
That's right. So that's right. So it was only based on the local channel busy measurements, and the proofs in the math that I've showed you here in the initial part of the section were all based on that assumption that all nodes were able to measure the same channel load. Other questions? Yes, please.
I'm not from this field, my information here is very limited. But for this information sharing, are you not going to use bandwidth? Is it not anything further forward?
So the question is the information sharing going to consume some of the bandwidth? And the answer is yes. We think it's negligible, though, because we're talking about messages that are on the order of 300 to 400 bytes. The information that we need to share is on the order of 3 bytes. So it's less than 1% overhead that it adds, but it's quite correct. Yes?
Can you say a bit more about the timing? How frequently are you measuring? You showed, the number of repetitions, but what is the timing in between measurements here?
Yeah, so we have used an update interval of 200 milliseconds pretty consistently. So in many of those convergence graphs, the x-axis was number of iterations. So you can divide that by 5 if you want it in seconds. So we're typically achieving 95% of our steady state value within about 5 seconds. And again, that's something we could tune. We think that that's an appropriate convergence speed. If we thought we needed to converge faster, we could, but a consequence would be higher steady state variations because of the noise measurements. It would be inducing more variation in steady state. Yes?
On slide number 18,
I can go back to that. Sounds like the beginning of a detailed question.
for the convergence,
Yes.
for different nodes, the message here starts for different initial, for the 0 second, it started with a different value. What was the reason?
The question is, why do we have different initial conditions here? The answer is, what we wanted to show was that it wouldn't matter. Even if we did have different initial conditions, we would still achieve fair convergence, and the convergence speeds would not be affected. So they're independent of initial condition. Why might you have different initial conditions? That's a good question. In many cases, you won't. In many cases, all of the vehicles will, if something changed, all the vehicles will be moving from one state to another state. They'll have the same initial condition. But you can imagine, for example, that you come around a curve and you join a neighborhood that already exists, and you've previously viewed the channel load as very low, so you're going at 10 hertz, and your friends are all maybe already here at 5 hertz. And so you have to be able to converge them, and you could even imagine that simultaneously that happens with another car that's coming into that neighborhood having seen even worse congestion. And so it was pushed down to a very low rate, and so it's trying to converge up at the same time you're going to converge down. That part of it is kind of artificial. We just wanted to show that initial conditions don't really matter. Other questions? Yes, Eric?
So measuring the channel busy ratio. So I guess it's the time when the channel is busy relative the total time of observation.
That's right.
So during these 200 milliseconds perhaps.
That's right.
So this would be comparing the incoming power with the threshold, I guess?
Yeah, so if your question is how are we measuring the channel busy ratio, yeah, so that thankfully that's something that standard 802.11 chips can already do. They're already capable of doing this because they already have to make a decision at every moment on a continual basis about whether the channel is busy or idle. So they already have to do that instantaneous measurement. All we need to do is integrate that over a period of time and divide by the interval of the time. So what we can do is we can query the chip and sample that. To be quite honest with you, I'm not sure how the implementers have done it, but we've had 2 successful implementations of this, and they were able to measure quite consistent views of what the channel busy ratio was. So I think that the chips are able to provide this information quite easily.
Right, but the follow-up to that this threshold, I think, is not something that each chip manufacturer or each vendor sort of tunes. Right?
Yeah.
So between chipsets, there might be different.
Yes, that's a possibility. So I'll repeat the question. If this is being done based on a chip's view of whether the channel is busy or idle, and if each chip uses a different threshold of detecting idle, or uses somewhat different logic for detecting idle, you could have inconsistencies from different vendors. This is true. This is something that we still haven't validated, because we do have 2 independent implementations that are producing consistent channel busy measurements, but they happen to be using the same underlying 802.11 chip, same vendor. So we haven't validated yet that we can do this across vendors. However, there is an 802.11 standard that dictates something about how you do this busy channel declaration. There is some wiggle room within that. It provides bounds. It doesn't provide precise rules. But the feedback we've been getting from the industry is that they all pretty much do it the same way. So there could be some small differences. We're hoping that those don't have significant impact. Another question here, yes?
You mentioned about sequential updates of the beacons. So I just want to know, like, you're gonna like assign the priority to the vehicle which gonna transmit beacons first or what?
No. So let me clarify. So the question was about the sequential updates. So first of all, it doesn't have anything to do with transmissions. It only has to do with update instance. What instance are we using for the update when we're doing our update from one node to another node? So let's say that we decide in a standard that everyone's going to use 200 millisecond intervals. All this means is that each vehicle can decide for itself when it wants to do its initial update, if you will, when it powers up, and then it just uses strict 200 millisecond intervals after that time. So what that results then is that every vehicle is effectively using a different phase within the 200 millisecond period for its update. And those are just individually decided. They don't have to be coordinated. But because they're using the same update period, then the sequence of updates will be the same in every period. If you were the first one in the current period, you'll also be the first one in the next period. And you'll be the first one in the next period after that. If I'm following you in the first period, I'll follow you in every period. And that sequential, and then we use the fact that it's sequential in our mathematical analysis to find the revised stability bound.
Okay, so like in the simulation, I'm guessing like the scenario is like more like urban, like on a highway scenario.
It's any scenario really. It just means that imagine that when your vehicle turns on, whatever moment you turn it on, that's when it does its first update of the day. And from that point on, it will always use 200 millisecond offsets from that time. When I turn my vehicle on, that's when I'll do my first one. That will set up some phase relationship between you and me. And when we encounter each other on the road, that phase relationship will still be there until we turn, they'll still be there all day until I turn my car off and you turn your car off. But it's independent of the road topology. It could be urban, it could be highway, it could be anything. So it's just a fixed phase relationship that comes out of whatever phase we've chosen independently, locally. That sets up a fixed phase relationship between us because we're using the same period.
So like 802.1p, many research are going on to handle this congestion. My question is general, did industry think to use LTE instead of 802.11p?
Okay, so that's a very different question. Let me repeat the question. So the question was, is there research going on into using alternate wireless technologies, for example, LTE, as opposed to this 802.11p type based technology? The answer is yes. And most people will tell you that probably those are complementary wireless technologies. They both have a role to play. I think the industry consensus pretty much is that 802.11p is the best choice for the low latency collision avoidance based types of communication that are motivating our work here. But if you're talking about getting traffic information or some idea of what is for sale at the next mall down the road, surely LTE could be a good choice for that. So in the general scope of ITS, or even cooperative ITS, LTE can have a role to play. But for safety, collision avoidance safety, at least in the US, the consensus is that 11p is the way to go. Is there another question? Any other questions? Okay, I think I've used up your time.
So I want to present with a small gift so you remember us. So thanks again very much for coming.
Thank you very much. Oh, thank you very much. I appreciate it. I really appreciated you coming today and your attention. Thank you very much. Thank you.
Yeah, thanks also to the audience for very good questions. And now I guess there's going to be a link where the presentations is available online afterwards. And in the same series, because John is also here, or he's not only here for the Halmstad Colloquium, he's actually also going to be the opponent for Katrin Sjöberg having her thesis defense this afternoon. And for this reason, there's another colloquium speaker coming almost at the same time. So tomorrow there's another Halmstad Colloquium speaker. I only remember the first name, Janos. Can somebody fill me in? Janos. And the last name is? Affiliation is? Vanderbilt University. Okay, so there's also going to be another colloquium speech tomorrow. And also I was going to ask whether you can fill in this IEEE list, because IEEE wants to know how many people attend the seminar and also how many of these are IEEE members. So if you can please fill it in. So otherwise, thank you very much.